Hi, in this video I'm covering section 6.4 on the real number system. So far we have studied the following sets of numbers. So we have done the natural numbers, which are the same as the counting numbers. We have mentioned the whole numbers. We did the integers. The last section was on the rational numbers. And we also saw that in a rational number, the decimal expansion either terminates or repeats. There are numbers that don't have that property, and those are called irrational numbers. So here's the definition from page 271. Okay, an irrational number is a number that is not a rational number and therefore has a non-repeating decimal expansion. And yes, there are a few examples of that. Some examples. Examples of irrational numbers. One is the square root of 2. The book does approve. The book proves why square root of 2 is not a rational number, but that's beyond the scope of this course. So I'm not going to go over that proof. But that's approximately 1.4142, 13562, and so on. But the decimal expansion will continue with no pattern, unlike rational numbers, where the decimal expansion repeats or terminates. Another example of an irrational number is the number pi. That's approximately 3.14, 159, 2654. But the decimal expansion will continue with no pattern. So in example 3, so you notice I'm not doing examples 1 and 2. Example 2, well, example 1 is a proof that the square root of 2 is not a rational number. So that's beyond the scope of this course. I'm not going to do that. And you're not going to be tested on anything like that. And in example 2, they ask you to approximate rational numbers. So again, I'm not going to do that. So series, series, that's again beyond the scope of this course. So I'm not going to go over examples 1 and 2. I'm going to start with example 3, where all you need to do is approximate some of these numbers. We're going to approximate the following numbers with a calculator, correct to 8 decimal places. Okay, the first one is 1 over square root of 2. So approximated to 8 decimal places. So let's check. 1 over square root of 2. You have the answer there. So to 8 decimal places, that's going to be approximately 0.70710678. B, we're going to approximate square root of 6 over square root of 8. And let's see what happens. Square root of 6 over square root of 8. So to 8 decimal places, let's write this down. That's approximately 0.86602,540. Or C, square root of 15 times square root of 5. That's about 10, well, that's 10 times the number we got before. So to 8 decimal places, that's going to be the square root of 15 times square root of 5. That's approximately 8.66025,404. And D, 5 square root of 3 plus 8 square root of 12. So let's try this. This is 5 times square root of 3 plus 8 times square root of 12. And to 8 decimals, this is approximately 36.36. 0.37 306696. Okay, so I'm going to read the properties of real numbers from page 277. Okay, so just let me type this. Properties of real numbers. Actually, I will copy this by parts. Okay, trying to make this fit. Okay, so I will start with the first 4. These are on page 277. Okay, the first property is the closure property. That says that the sum of two real numbers is a real number, and the product of two real numbers is also a real number. Like 3 and pi are both real numbers, so 3 plus pi is a real number. And 1/2 and square root of 3 are real numbers, so 1/2 times square root of 3 is also a real number. The second property is the commutative property. If A and B are real numbers, then A plus B equals B plus A. And same with the multiplication, A times B equals B times A. The next property is the associative property. If A, B, and C are real numbers, then it's the same if you add the first two and then add the third one, than if you add the first and then the sum of the next two. And with multiplication, works the same way. In other words, the way we group the numbers is not important. And with the commutative property, the order in which we combine the numbers is not important. Number 4 is that 0 is an identity element for addition, and 1 is an identity element for multiplication. So if you add 0 to any number, or you add any number to 0, the result is going to be that number. And if you multiply 1 by any number, or any number by 1, you are going to get that number A. And the last two. Are the additive inverse and the multiplicative inverse. If x is a real number, then the opposite of x is an additive inverse. That is x plus its opposite, or the opposite of x plus x is going to be 0. And if x does not equal 0, then the reciprocal of x, or 1 over x, is a multiplicative inverse for x. So 1 times the reciprocal, or x times the reciprocal, is 1, and 1 over the reciprocal, 1 over x times x is going to be 1. And the last one is that multiplication distributes over addition, which actually I mentioned before when I did sets. If A, B, and C are real numbers, then A times B plus C equals A times B plus A times C. So in example 7, you need to identify the property being used. So we're going to do examples. We're going to go over example 7. Okay, so I'm going to copy all parts. And then the next. We have 7 more. We're going to identify the property being used in each of the following statements. That's example 7 on the same page, or the same pages. Starts on page 277 and page 278. Okay, the first property. 3 plus 4 is an integer. So the sum of two integers is an integer. That's the closure property. Square root of pi, or square root of 2 plus pi, equals pi plus square root of 2. This one is the commutative property. Disclosure property of addition. So I'm going to type them. I'm going to make, there it is. Okay, trying to make this fit. Okay, I'll give it another try, but I'm trying to keep it at the same level. Okay, so let's try that. Okay, so part A, 3 plus 4 is an integer. This is the closure property of addition. B, square root of 2 plus pi equals pi plus square root of 2. This is the commutative property of addition. Part C, 0 plus 3.6 equals 3.6 plus 0 equals 3.6. So 0 plus any number, or any number plus 0 is going to be that number. This is the 0. This is the fact that 0 is the identity element for addition. Is the identity. 0 is the identity for addition. D, you are grouping the number that you're multiplying. This is the associative property of multiplication. E, a number plus its opposite is 0. This is the fact that the opposite of x is the additive inverse of x. F, a number multiplied by its reciprocal is 1. This is the property that the reciprocal of x is the multiplicative inverse of x. And G, this is the property that multiplication distributes over addition. Okay, so a few more examples. These are exercises on page 279. Okay, so we have a few statements. We will determine which of the following are true or false. And if a statement is false, we're going to give a counterexample. Let's start with number 37. Number 37 says that the product of two irrational numbers is irrational. Okay, this is again page 279. And this statement is false. If the statement is false, give a counterexample. So one example can be square root of 2 and square root of 8. These two are irrational numbers, but the product is a real number. So these two are irrational. But their product is a rational number. Square root of 2 times square root of 8. This is square root of 2 times 8. But the square root of 2 times 8 is a square root of 16, and square root of 16 is 4. So we have two irrational numbers whose product is not irrational. And as a note, all non-integer square roots such as, and I need to write this a note, unknown integer square root, such as square root of 2, square root of 2, square root of 3, square root of 4 is 2, so that's not a, that's an integer square root of 5, square root of 6, and so on. Square root of 9 is 3, but the next one would be square root of 10, are irrational. That's how I knew that square root of 2 and square root of 8 are irrational, but their product is not a rational number. The product is rational. Number 40. If n is any positive integers, then the square root of n is irrational. The answer is false. So this statement is false. And a couple of counterexamples that I can quickly think of are square root of 4. 4 is a positive integer, but the square root of 4 is 2. And another one, square root of 9. Square root of 9 is a positive integer, but the square root of 9 is 3. Or square root of 16. 16 is a positive integer, but the square root of 16 is 4, which is rational. And those are just a few examples. And number 42. If n is any integer, then the square root of n squared is a rational number. Well, this one is true. Okay, so I will do a couple of applications on the consumer price index or CPI and the house price index or HPI. So two applications are the consumer price index, also known as the CPI, and the house price index, or HPI. Okay, so we're starting with the consumer price index, with the CPI. That's on page 275. The consumer price index is a measure of the average change over time in the prices paid by urban consumers for a market basket of consumer goods and services, including items such as food, clothing, housing, transportation, and medical care. The base for comparing prices with the CPI is the year 1984, when 100 worth of goods and services cost 100. And every year, the CPI increases. But for you to have an idea, we have this table. So the consumer price index, how it's been increasing throughout the years. Okay, so let's, I'm going to do number 68. on page 207, on page 280. We're going to use this table to answer the question. So a car cost $30,000 in 2015. Question, what would its price have been in 2020 dollars? So from the table, we can see that the CPI, the Consumer Price Index, in 2015 was 237. And the Consumer Price Index in 2020 was 258. So we're going to take the ratio of the Consumer Price Index in 2020 and the Consumer Price Index in 2015. This is 258 over 237. That's approximately 1.09. This means that on average, things cost 1.09 times as much in 2020 as they did in 2015. So this particular car that cost 30,000 in 2050, in 2020 cost 1.09 times as much. Okay, so we're going to multiply 30,000 by 1.09. And this is going to be 32,700. So the price would have been that in 2020 dollars. The price would have been $32,700 in 2020 dollars. So that's one application, and we're going to talk about the CPI in chapter 8. We're going to continue with that. And the next application is the HPI, or the House Price Index. That's the other application. This is on page 276. So the house prices are not consistent throughout the country. That is, a similar house in Atlanta is not going to cost the same as a similar house in Denver. Like the price of the price of a house vary throughout the country. Like house prices in Denver are not the same as in Atlanta, and they are not the same as in Nashville or as in Philadelphia, and so on. So we have this table on the same page. They show you the HPI in some of these cities, in Boston, Las Vegas, Miami, San Francisco, and Dallas. Not surprisingly, the highest price index is in San Francisco. That's one of the most expensive places to live. So it has some of the one of the highest HPIs. So we're going to go over example 6. And by the way, this is just an exercise. This is not a reflection of reality. In the sense that a house in Boston doesn't cost $120,000. So let's think of this as an exercise only. Or maybe that was true in the 90s or so. But let's suppose that you own a house in Boston that costs $120,000. What would be a comparable house cost in Las Vegas? We're going to consider the HPI. So the house price index in Boston is 183.6. And the house price index in Las Vegas is 144.8. We're also going to take the ratio. Take the ratio. $144.8 over 183.6, and I'm taking it like that because the price is going to be the cost is going to be less in Las Vegas, and that's approximately 0.79. With that, we know that now we can tell that a house in Vegas costs about 79% of a similar house in Boston. So we're going to multiply 0.79 by the hypothetical price of a house in Boston. And this is 94,800, which again is not realistic for a house in Las Vegas. That's just an exercise. So that would be a comparable house cost in Las Vegas, 94,800. So this covered section 6.4, and I'm going to stop here. Thank you for listening.